Hello, we will create a rollup pattern from scratch. We will do this in the new project. This rollup pattern will be for the battery cells power rollup. So we will roll up power of battery cells to the battery. And first of all, we will create pattern, right? So or maybe first of all let's create the model, right? So let's create block definition diagram, and here we have battery, and we have cell, battery cell, and we can say that we have some specific number of those cells, like let's say like 8, let's say. And now this will be our model, right? So let's put it into the data package, and now let's create another package for our pattern, rollup pattern. And here let's create block definition diagram. Let's create our pattern. So this pattern will allow to roll up the power of the cells to the battery. So first of all, when we create the power roll-up pattern, we need to create block with the pattern stereotype. So this will be to hold the property values and the constraint, and all of it required information like a parametric diagram to roll up to calculate properties of roll up, battery power roll up pattern. So any name, right? And it is important to say that this is our pattern, so we need to stereotype it as the pattern. Otherwise, we would not see this in the pattern list. So this is pattern apply. So now we need to create properties which will exist in this battery and the cells. So for that purpose, we will create value properties, and this will be required properties. Good state. So is this good state of the battery? Then those state of charge, and SOC, and VOC is open-circuit voltage in volts, which is computed based on SOC and good state. So then number of cells, and now if we want to calculate something only for the battery, and we want that those properties would appear as a part of the pattern, so we can do this, or we can leave that as the specific properties of the battery. But let's put everything inside, and then later we can discuss. So for example, voltage of the battery. So okay, so we have all properties. Now we need to create constraint block which will calculate the logic of the pattern. Will hold the logic of the pattern and will calculate the required values. So here we created constraint block. It will be, let's call it total, or this could be whatever name, and we will paste this code, which will do all the calculations. So here in this code we see what's happening. So first of all we take we check that we have childs, and if we don't have childs, so we calculate voltage from this expression. If we have childs, so we will check the else statement. So then we will calculate voltage by summarizing the voltage of the childs, and also we will sum the good states of the battery cells into the number of cells. So good state can be 1 or 0. So if it is like 1 1 1, so we will have 3 cells, right? And then if there is childs available, cells available, and the number of cells is more than 0, then we will say that good state is equal 1, and this will be performed when we have the battery, not the child, right? Because we say that child's number is more than 0, right? And then we will calculate state of charge by summarizing the child's cells state of charges and dividing by number of cells. If actually number of cells is 0, but we are not a child, we are not the cell, but we are the battery, so we will set the good state to 0, and state of charge we will set to 0. And in any case we will perform total voltage at the battery level calculation, as we see here at the battery level, and this will be voltage of the some voltage of the cells, and then resistance of the battery and the current of the battery. And so this will be calculated in any case, right? And this is not a part of the roll-up pattern, and we could move this one into separate parametric diagram, which would be created in the batteries, not as a part of the roll-up pattern. But if we want to keep it dynamically recalculated, if there's, like, for example, batteries used as a cell in another kind of bigger battery, then we can leave this as a part of the pattern. Okay, so now let's copy this code, and this is GPython code, and let's create this as a expression. So I pasted it, and we'll set the code language to this Python. The only problem is with GPython that you need to be careful with the spaces. So in order to be sure, I will just update the spaces. It looks like all of them are okay. If there's something will not recalculate, then I will delete the spaces. Okay, so looks good. So this is any logic, right, which will be used in the pattern. Now next step is to parse parameters, right? So I parse parameters in order to get those parameters here, and now I got those parameters here in order to be able to use them to connect to the value properties. And one more thing, you see that some of them is for example voltage is with sub, right? And then good state is with sub, and then also state of the charge is also with sub. And we use this additional parameter, then we need to take the information from the child. So if we need to take any information from the child, like for example some of the child property values, right? So we need to create need to have additional parameter in order to be able to know what we are referring here. For example, like sub voltage, right? We can't say voltage here, otherwise we would not know which voltage. Is it of this battery or is it of the child of the battery, right? So this in this case we need another parameter here. Okay, so almost done. Next we need to create a composite association to self, and this will hold information that this pattern will be applied recursively, and we can refer to the child properties, and we can call this role as, for example, sub power. Doesn't matter, this name doesn't matter, and it should be multiplicity many, and it should be union is derived union close. Okay, so now next step is to create parametric diagram inside of the pattern, in which we will bind those value properties of the pattern to the constraint. So I'm going to block, I'm creating, and now from the sub power I will take good state, this one and this one. So those I will reference to coming from the child of the battery. Everything else will come from the battery itself. So now I got this one, and now I need also constraint, right? So I will need constraint. So let's bring, and we will map manually. So okay, what I need those properties parameters here that will map to the specific properties of the battery. So we and then I need from the child good state, sub good state, right? And then sub state of the charge and sub voltage. So those I will bind to the child properties, to the coming from the child, and this one will be here. And now I need this one. Actually, this one should be this one. Okay, this will be this one. Number of cells, this one, right? Number of cells, and then good state. Okay. Okay, so now we have almost everything. We need here multiplicity, that could be many of them. So let's specify multiplicity as many here. Same here. And same here. Okay, by default multiplicity is 1, so we can skip this step to specify multiplicity as 1. And it looks like okay. Looks like everything okay. Okay, let's save our project. File, save project as battery Rollup. Okay, on desktop, save. Now let's go to our model, and we can apply this pattern. So let's right click on the battery, tools, supply rollup pattern, choose the pattern, battery power rollup pattern, create values, okay. And we got this pattern applied. So we have also some properties on the cell which are not used, like those properties will be only for the battery, but we can ignore them. And this is because we created the pattern, those properties in the pattern. So if we want that they would be recursively available, so this is the only way to do that. Okay, now we can right click and simulate run. And I will move this dialog here. It will be easier to see. I will close this one. We'll close this one and this one. So I will need only this one. And let's see. And also in console, I will check that everything runs correctly. Initial solving complete, everything looks okay. Okay, so now I can see that I have 8 cells, right? And I can update properties of those cells. So for example, first cell, good state is 1, and everything is recalculated. So based on this pattern, this logic, right? So okay, good cell 1. So we see that it works. I can state of charge, specify state of charge. You see that the state of charge is recalculated, voltage is recalculated, everything is recalculated. And based on, so pretty much that's it. So pattern works. And here we see this ability to specify the state machine as part of the pattern. So we can do this also. So let's stop this execution. We can create inside of the pattern block state machine. Create diagram state machine, and this will be normal and failed. Okay, normal failed. And now we see that good state in one case is 0, in one case is 1. And it's on off. Okay, so let's do that. It's on, so to failed, and off to normal, right? So now we can specify what will happen in those states. So we will go to on entry to the opaque behavior and body and language, and we will specify good state equal 1. Okay, normal. And then here we will specify body and language equal 0. Okay, so now instead of this specifying failed and good state by 1 and 0, we would execute this system, and here we can choose what will be the state. And when we execute the system, we need to run behaviors, and we will get immediately the state of every component you see when every cell is a normal, right? Then we can select it and say, so normal by default we get everyone to 1, right? But at any moment we can select and say it's on, so it will be updated to 0. And then we can track voltage and time series chart, right? So we can open this time series chart, we can track it, so we can go through them, and okay, so this will be on, this will be on, this will be on, this will be off, this will be off. Okay, that's it. Thank you.